In example 3, we've got a scientist who's taken 30 observations of the masses of two reactants in an experiment, and she calculates the product moment correlation coefficient and finds out that the sample correlation coefficient is minus 0.45. So if we just draw a little sketch of what's happening here, say X is the mass of one of the reactants in the experiment, and Y is the mass of the other reactant in the experiment, then out of the sample that she's taken, our sample correlation coefficient is minus 0.45. So there's a weak correlation. Let's draw out the scale of correlation coefficient. So in the middle is 0, where there would be no correlation, and on the right we'd have a strong positive correlation, and on the left we'd have a strong negative correlation. So we're at minus 0.45, somewhere here. So the scientist believes that there's no correlation between the masses of the two reactants. So the scientist believes that that's close enough to 0 to conclude that there's no correlation. And we're asked to test at the 10% significance level. The scientists claim that there's no correlation, stating our hypotheses clearly. So H0 is always the same. H0 is that rho equals 0. And just as a reminder, rho is the population correlation. So let's write that. The population correlation is 0, i.e. no correlation. And our alternative hypothesis, well, our alternative hypothesis will change based on the question. So in some questions it might say test the claim that there's a positive correlation, in which case we'd put rho is greater than 0, or it might say test the claim that there's a negative correlation, in which case it will say rho, our alternative hypothesis would be that rho is less than 0. In this example, we're not told that we suspect that there's a positive or negative correlation. All we're asked to do is test whether rho is 0 or rho is not 0. So our alternative is that there is a correlation, and in which case rho could be anything other than 0. So let's put that in a bracket, that the population correlation is not 0. Because if rho is any other value other than 0, then it is correlated. If it was if rho is 0.1, it would just be a weak positive correlation. Now this is called a two-tailed test because we're not told that we suspect that it's either positive correlation or a negative correlation. Our critical region is going to include both this side of our scale and this side of our scale. And because of that, we're going to split this 10% significance level, and we're going to put 5% significance on the right hand side and 5% significance level on the left hand side. So let's write that down. So 5% significance level in each tail. And what I mean by tail in this case is on the left of our scale and on the right of our scale. So we'll bear in mind that our significance level is 5% at each end. So if we go to our table and we find n equals 30, because our sample size is 30, and we're looking at that row. And we need to look at the 5% significance level, because this significance level is how much is there at one end of our scale, or at one end of our distribution. So that's 0.3061. So what that means is that in order to conclude that there's a positive correlation, our value of R would have to be greater than 0.3061. So our critical region for the positive side would be that R has to be bigger than 0.3061. Now notice that these tables only have positive values in. Well, it turns out that that's because the distribution is symmetrical. So our critical region on the left-hand side for concluding that there's a negative correlation is exactly the same, but we put a minus in front of it. So our critical region on the left-hand side would be less than minus 0.3061. And that's our critical region there. And we can conclude, if we're to the left of that point, that there's a negative correlation. So in this case, R is equal to minus 0.45. So we are in the critical region, so we can conclude that we're far enough away from zero to say that there is a correlation. So let's write that down. Minus 0.45 is less than minus 0.3, and by that we mean it's further away from zero, or closer to minus 1. So sufficient evidence to suggest that there is a negative correlation, sorry, not a negative correlation, there is so sufficient evidence to suggest that there's a correlation between the masses of the two reactants. Now you'll notice that I'm not concluding that there's a negative correlation, I'm just saying that there's evidence to suggest that there's a correlation. That's because our alternative hypothesis is that there's no correlation. So you need to make sure that your conclusion matches your alternative and hypothesis. We weren't testing for rho being less than 0. And it's always a good idea to conclude in context. So here I didn't just say there's evidence to suggest that there's a correlation. I've put it in context and said correlation between the masses of the reactants. It might be interesting to look at this example again, and instead let's pretend that the scientist believes that there is, rather than no correlation like we did before, let's suppose that they believe that there's a negative correlation. So H0 is still that rho is equal to 0, that should be rho, and our alternative this time is that rho is less than 0, that there's a negative correlation. So let's draw out our diagram again of the scale of correlation from -1 up to 1, and in the middle we've still got no correlation, and on the right we've got a strong positive, and on the left we've got a strong negative correlation. So we've still got R equals minus 0.45. The only difference now is because this 10% significance level is all going to be in the left tail of our distribution, because we're not bothered about whether we can conclude that there's a positive correlation, because we think there's a negative correlation. So this 10% significance level, we're not going to split it. And we're just going to look at our table with n equals 30 at the 10% significance level, which is 0.2407. Now, you'll notice that that's a positive number, 0.2407. And if we were testing for positive correlation, R would have to be bigger than that number, so to the right of that number, to conclude that there's a positive correlation. Well, remember that it's symmetrical about 0, so actually we don't need another table to tell us that we'd have to be less than minus 0.2407 to conclude that there's a negative correlation. So because we're closer to minus 1 than minus 0.2407, we're in the critical region, because our critical region for concluding that there's a negative correlation would have been to the left of that number. So let's write that down. Minus 0.2407 is less than minus 0.45. Sorry, I've done that the wrong way around. Minus 0.45 is less than minus 0.2407. So we can say that there's sufficient evidence to suggest that there's a negative correlation between the reactant masses.